Hello guys, welcome to Algorithms Made Easy. Today we will be discussing the question convert BST to greater tree. If you haven't already watched the first part of this video, I'll highly suggest you to watch that and then we can move forward with the third and the final solution to this problem, which solves this problem in constant space. The approach that we will be discussing over here is called Reverse Morris In-order Traversal. We'll see how we can apply Reverse Morris In-order Traversal in this problem with the help of an example. So suppose this is the tree given to us. In the previous video, we applied reverse in-order traversal in order to find the solution. So the solution still remains reverse in order, but how we can apply it without using any extra space is what we will achieve over here. For every node, we have two pointers. One is the left pointer and other is the right pointer. So when we try to visualize this pointer, it will look like this, where every node has two pointers. Some of these pointers are pointing to a null value at this point of time, and we will be using these null pointers in order to point them to their successor or their predecessor. Now, suppose we are at this node 8. When we are at this node 8 and have done our computation of changing the value of this node 8 with the sum of all the values that are greater than this 8, we need to move to the node 7. So rather than maintaining a recursion stack to do that, we can change the pointer of this 8, the left pointer of 8 to 7, so that we can easily move to 7 without using any extra memory. Now, suppose we are at this node 5. In this case, rather than moving from 5 to 6 to 4, as we have computed all the nodes in the right subtree, we need to move directly to 4 without going all the way to 6. Then we can update the pointer of this 5 to 4, and that way it will be easy for us to move to the next node. This is just to give you a brief idea as to why we are changing the pointer. Now let's see the actual implementation. Coming back to the original state of the tree, we are at this root node 4. And now we need to find the smallest value which is greater than the 4, because that will be the value from where we need to come to 4 directly. So when we find that value, we find it to be node 5. And when we reach this successor node 5, we update its pointer to directly to root node. Now we move the root to the right hand side, as we need to first traverse all the way to the right and then move to the left part. When we reach this root node 6 now, we again do the same thing and find the successor which has the smallest value which is greater than 6 and which turned out to be 7. So we update the pointer of it and then we move the right node. Then at 7 we again do the same thing and update the left pointer of 8 to 7. Now when we are at 8, there is no successor left as it is the rightmost node. So that means we need to now traverse back. We'll take a sum variable which will hold the sum of this root value, update the node with this sum, and then as in any InOrder, we know that if right doesn't exist and we have processed the root, we will now move to the left part. So now we move root to root.left. So we reach 7 again and the sum is now 8. Now as the root is at 7, we again try to find the successor, but this time the successor 8 already has a left node, which signifies that we have already visited it. So we won't be visiting it again. And this is the case where we update the value of this root node with the sum value, that is adding it to 8. And then we update the sum to 15, move a right node to the left of the 7 and do that continuously till we get the root node as null. When the root node is null, that is our answer. And then we return the actual root. Now, it is a bit complicated and it will be more clear to you when we do the coding part. So let's see how we can code this. So as discussed, we'll start off with checking if the root is null or not. If it is not null, then we can simply return null. We need to have a sum variable. And now as we need to return the actual root as a result, we will take this root into another variable called node. Now we need to loop till this node value is not null. So there can be two cases, either there is no right tree or there is a right tree. So now, if there is no right tree, that means the node dot right is equals to null. So this is the case when we reach the rightmost node, which is 8. So in that case, what we did is we just update the sum with the node value, update the node dot val with the sum value, and move our node towards the left pointer that we had. What about if there was a right tree? So if there was a right tree, we need to find the successor of it. That means the smallest value which is greater than this node value. So in order to do that, we can have this value into a successor. We can have a next greater method. We pass node into this and it will give us the next successor value. Now we'll implement this method in the later part. Suppose we are getting the successor alright. Now in the successor, there can be a scenario wherein the left is null. That means it is unvisited or it is not null. That means it is already visited. So in order to check if it is null, that is it is unvisited, in that case we were updating the left pointer of this successor to the current node. So the left of this is our current node and the node should be moved to the right like we did. Else, if it is an visited node, we need to first break the link that we have previously created, that is the successor.left link needs to be deleted. Now we need to update the sum with the value of the node, updating this value with the current sum that we have and moving this node to its left. So this completes the part. The only part that now remains is implementing this next greater method. So inside this next greater method, the next greater element will be the immediate right node of this current node. So we'll have this as the successor. If there is a left subtree of this successor, we need to go all the way to the left and that will be the smallest next greater element with respect to this current node. So we will have a while loop till the successor dot left is not null and also the successor dot left should not be equals to this current node value. We'll move the successor to successor dot left in each iteration and at the end we'll simply return the successor. So why we are doing successor dot left is not equals to node. So there may be a case where the successor already have a left pointer pointing to the node and in that case it will become an infinite cycle. So in order to get away with that, we are doing this. This completes the coding part of this problem with respect to reverse Morris in-order traversal. When we run this code, it gives us the right result. Let's submit this as well. So it got submitted. The time complexity is O of n while the space complexity is O of 1. If you want to learn more about Morris traversals, we have made a video solving one of the questions using Morris pre-order traversal. So please have a look. Thanks for watching the video. See you in the next one.